Cool. Not too bad, right? Okay.
Just takes a while.
Yeah, it takes a while. So luckily that was the last one in Ultra VSI. There will be more in cadence. But I'm not. So see here, I'm trying to balance everything. If I want you guys to work on a lot of hands-on labs, use the industry standard tools, I will not teach new things and give you homework assignments in these lectures. So we'll just meet over there and work on your labs. Okay.
That's great.
Yeah. It's fire. And so for the quiz, so we have one more inverters over here. One more inverters. And so that's the voltage we want to use for this inverter, and it uses this point. Here's the output. So I saw a bunch of issues. So during the first cycle, you are getting VTHN loss for these points. Sorry. That's correct. Yeah. But after the first cycle, because this one will swing around VDD minus VTHN and 2 VDD minus VTHN, so whenever this guy is reaching that 2 VDD minus VTHN, right, it's a 2 VDD something, which means this guy is pushing and this is pulling, right? So this is pulling because this is short to the gate, and whenever this is being pushed to the higher voltage, and this gate is widely open, so that's why the next cycle it pulls from VDD. It will be able to pull the entire VDD to this point. Does that make sense? This is VDD. So whenever this guy is at 2 VDD minus VTHN, which means it's getting pushed, right? So it's pushing. This is pushing, this is pulling. This is pushing, this is pulling, and pushing, you are getting 2 VDD minus something, and that's short to the gate. And that means the gate will be widely open, and so you are able to pass the entire VDD to this point. So after the first cycle, this point becomes VDD, not VDD minus VTHN anymore. Okay? So, and then when it pushes again, it will directly push to that 1 VDD, so it becomes 2 VDD. If this becomes 2 VDD whenever this is pushing, so this is widely open, so when it pulls, it will be able to pass the entire VDD over here, and next time it pushes, it becomes 2 VDD. So both points are swinging around between VDD and 2 VDD after the first cycle, eventually. Keep that in mind. So it's 2 VDD, a VDD and 2 VDD over here. Alright, and because this one, remember the PMOS, and there's no issue about the wire connections and everything for the NMOS, but there is a potential issue for the PMOS, that you need to place the PMOS in its individual wire, right? Because this is the source, you only care about the source. Doesn't matter source or drain, but just one terminal of the channel. Okay, if this one has a voltage higher than the highest potential of the circuit, as 2 VD, which means this point need to be taken care of, okay? And this transistor need to be taken care of. The reason for that is if your P, because for other N wells, for other P transistors, their N plus are shorted to VDD. Remember when you design the reel-to-reel layouts, you have a lot of things inside, and all these top reels are shorted to VDD. Okay, so which means all the other circuits, I'm just drawing one PMOS, but all the other PMOSes, their N well tap is shorted to VDD. Okay. So if you have a source here is potentially getting to VDD, and if you have a universal N well, and it's gonna forward bias this PN junction over here and eventually causing body effect for this PMOS. So that's why we wanna separate the P well as an N well of this PMOS. Okay, by just having an individual N well, don't make the connection. Okay, it's still the same wafer, but don't connect them. So the N well of the red circuits is over here, and this PMOS's N well is just over here, just individual N well. And you can see it should be shorted directly to its source instead of to VDD. Remember all the PMOSes we usually do a connect to VDD, right? Connect to the top to VDD, but this one is different. This one should be shorted to the source, because the source will be the highest voltage in the circuit. So because this connection is the body connection, is the N tap, so it's basically just a simple connection like this. All right, so in your layout, okay, you short your gate, right, for this inverter, and you don't want to label this a VDD. Just don't label it as a ZD, and you want to short your source to the body, because that's the N tap. Okay. And this to here, right? And this to here. Any question on the quiz? Probably not. Let's move forward. So that's the circuit you want to use for the sample and hold, right? So the sample and hold circuit looks like this. You need these basic components here. You do this, cross it, charge pumps. And here's a signal line. You have another NMOS here, and that takes this voltage, and you got a capacitor, and this one shorted to ground. And from this point, you got a PMOS. That's a protection NMOS. That's the NMOS to reset. And that's the face of it. And this one is directly shorted to NMOS to VDD, so it's always open. And for here, we need a little inverter here to pass the signal to the gate of the PMOS, and the signal here is called phi. Okay, and this one goes to VDD. We need an NMOS here. And that's a sampling capacitor. And this one shorted to here. This one shorted to the drain. And this gate shorted to these gates. So that's the entire sampling sample and hold and track, sample and track and hold circuit. How this works, right? So that's a question. And the face over here is phi naught. Phi naught. So same face. And that's the inverse of it. Okay, you can easily just add an inverter to invert it. So we already understand what's going on for this circuit. So after the first cycle, this voltage becomes what? VDD to VDD, right? And we're basically using that voltage because this is from this gate and directly shorted to this is the NMOS, keep in mind, this is NMOS. So NMOS over here. So what's the point of having VDD to VDD over here to the gate of this NMOS? We have done similar things. We know that we want to turn this widely open so we can pass the whole VDD to this point, right? So now let's look at the phase, when that happens. So if this point is VDD, what's going to happen? So this phase is what? It's pulling, right? If here's 1 VDD, it's not minus, oscillating. If you are getting 1 VDD over here, this guy is pulling. It's a falling edge. Okay? This NMOS is on or off? It's a falling edge. It's off, right? If it's off, which means there's no channel to go to the ground, so it's not able to pull anything, right? Even though this is on, it's okay. There's no falling edge, so it's not pulling anything. All right, so there won't be any current going through the cap. If it's 2 VDD, which means this guy is pushing. It's a rising edge. This rising edge is going to turn on this NMOS. Okay, so this channel is on. It's a short to the ground. So we are forming a channel to allow the current to flow. So what's happening is, if this guy is 2 VDD, because the top here is a power supply, it's just VDD, right? It's a universal VDD of the circuit. So whenever this guy is 2 VDD, this NMOS is also on. So what's happening is it's going to dump all the charges to the cap, and the voltage will be stored across the cap. And what is the voltage being stored over here? And why? The gate voltage here is 2 VDD.
Yeah. So 2 VDD minus VTH.
How much you can store over here? This is widely open. It's larger than 1 VDD, right? So you should be able to pass the entire VDD over here. Right?
Yeah.
You should. Okay, that's the whole point. That's the whole point of using this charge pump, because we have a 2 VDD, so we can pass the entire VDD over here. So not minus VTH anymore.
So it's just 2 VDD?
Just 1 VDD, because you only, so on the other side of on the drain power supply, you only have 1 VDD available. So the gate is just the switch of the faucet, right? You just turn it wide open, so you are able to pass the whole VDD to the cap. Okay, it's not decreasing or subtracting the VTH from it, because whenever you are having this point charged up to VDD, what's the VGS over here?
It's 2 VDD on the gate. And
Yes.
then there'll be zeros on
No, you are passing the whole VDD to this point. So what's the VGS?
the VDD.
VDD. Is that larger than VTH? Yes. So it's still open. So you are able to pass the whole VDD here. No problem. Can you get a VDD plus VTH over here? No, you only have VDD available on the power rail.
Yeah.
Whereas you cannot get larger voltage from this point. So the whole thing getting passed through here is just VDD. Okay? And the next cycle, you got a VDD here, and which means this guy's pulling, right? This guy's pulling, so it's falling edge. The falling edge to the NMOS, this NMOS is on or off?
Oh, it's
Falling edge, on or off?
off.
Off, okay? So did you store a VDD across the cap previously? Yes, because you turn it on, it pulls. And this was on, so it pulls. Like whenever this is on, you can imagine, right? Even though it's just drawings on the paper, but it's actually something happening. You turn it on, so the NMOS at the bottom get a channel open, right? and then you got a 2 VDD over here, starts dumping charges, boom, dumping on the cat, right? So the capacitor is full with a bucket being filled with water. Are you discharging it? No. So it's staying there, and then you just cut it at the bottom, so the NMOS is off. You still have the bucket of water storing there, so it's called a floating VDD. Floating VDD. It doesn't have a source to back it up. It's floating. If you discharge it, it has a finite amount of charges. It will be gone. If you are discharging a source, depending on the power plant, right? You'll still have coals to be burned to create the power. But it's a floating VDD in the bucket. It's staying there. It's a VDD. Okay? You got a VDD over here. So during the cycle that it stores the VDD, which means whenever this guy is, I'll just let you guys tell me. Whenever this guy stores the VDD, because it's not pulling, right? It purposely charges the VDD and this guy is turning off. So what is phi naught signal? Phi naught, this line, is what? To create that floating VDD.
This would be 0 to turn on NMOS.
It's a 0 here, so phi naught is 0, right?
Yeah.
So this is also 0. Okay? It's the same phase. This is all 0. Is this NMOS turning on or turning off if this is 0? Turning off. So which means it's not grounding this point. Okay, it's not grounding this point. So it's blocked. So it's blocking this point from shorting to ground. And also, what about this one? This NMOS, the gate of the NMOS is shorted to VDD. So this guy is always on. According to the paper published in 1999, this NMOS is just used as a protection NMOS to avoid all these surges when you discharge and charge and discharge. So avoid the surges coming from the ground to reach to this point to damage the gate over here. So it's just for protection. So this guy's always on, always on. Don't worry about that. The phases are not affecting this guy. So it's basically blocking this point from grounding, from shorting to ground, if this is off, right? If the whole thing here is off. So which means this point is not being reset. You agree with me? If I turn on this NMOS and this NMOS is always on, I'm actually resetting this point. You can see this point is actually shorted to this NMOS. And here is the sampling point. That's the analog voltage input. Remember the paper shows you that you want your VGS here and here. That's VG, that's VS, right? So you want VGS to be what?
Greater than
To be VDD. No, to be VDD for this case, for the sampling transistor.
Yeah.
Why? Because it's constant VGS. It's a constant VGS. So when signal goes up, your VG should go up at the same time, but having a VDD as an offset. So it's basically VG equals VDD plus VS, which is the signal. Oh, let's still go VSIG, okay? And VS is what over here? VS is VSIG because it's short to the signal.
Yeah.
So VGS is what?
VDD plus VC. Yeah.
That's how we make a constant VGS, which is required. Otherwise, it's gonna cause distortion to the sample signal. Remember, because of the RC delay, if you are having a inconsistent VGS, you are having inconsistent RC delays, and your signal will be distorted. So that's the whole point. Keep in mind, that's the goal. Okay, that's the goal. So the whole circuit here is trying to create a constant VGS for this single transistor. That's the whole point. Okay? So now, we are talking about whenever this is off, and this is storing a floating VDD, and this is off because this is off, right? So both are the same phase, and this is off as well. Okay? Floating VDD over here, that's a floating VDD. And that floating VDD will be added, or this signal will be added to the floating VDD because the signal here will pass this pass gate signal here and adding a sound wave to this point. Because the signal is you can consider as a signal source. Okay, it's a little voltage here, and it's adding this signal, this voltage to this point, and because we have VDD over here, it's a floating VDD, and this signal, AC signal, will be added to this DC signal, and eventually the voltage here will be what?
Yeah.
Compared to ground. Does that make sense?
Yeah.
So the point, the voltage here will be less, equal, or larger than VDD.
Yeah. Well,
It always happens, right? If it's subtracting, it's pooling, then it could be less than VDD. But there will be a chance that it will be added to VDD, so it becomes larger than VDD. So this PMOS needs what? In its own well. So in schematic design, what you want to do? Okay. But if you compare this one to the quiz, actually, this PMOS position is very similar to this one, right? It's just the PMOS shorted to this point.
yeah.
It's the same thing. So so we are talking about these two are off, right? So right now, so these are off, right? Still. So if phi bar is 0, so phi will be what? 1. So for this little inverter, is phi is 1, which transistor is on? This is on.
Yeah.
If this is on, this signal will pass this pass gate and eventually reach to this point and reaches here. Okay? And you are saying there may be some loss. So that's why we have another one over here to prevent any losses. So we'll talk about that later. But you can see this is the pass gate. So the signal voltage will goes to here. Yes, it's going to be added to VDD, but also this NMOS is on. It's going to go through here and reach the gate of the PMOS. So what's the VSG of this PMOS?
Would be the SG would be VDD.
Yeah.
Right.
Is it on or off?
It's on.
On, right? So this is different. We always use a 0 voltage, gate voltage to turn on the PMOS, but now, because we have a larger source voltage, so you can have this one not at 0, but still have this on, because VDD plus V6 minus the gate voltage as VSG for the PMOS is going to be what? VDD,
Yeah, VDD.
which is larger than VTHP. So this guy's on, the whole thing here will be passed to this point. So the voltage here is what?
That's VDD.
Wait, VDD or VDD plus V6?
Wouldn't it be VDD?
V.
Yeah, because wouldn't it be VDD because
Oh, VDD, yeah.
Yeah, because it's VS.
No, the whole thing. The whole thing. Remember you just consider this guy as a 0, right? So the PMOS is good at passing VDDs.
Yeah.
So the whole thing can pass. So it just verifies the other side. It's still the same thing.
Okay.
If this is S, this is G, you are getting VSG to VDD, still opening, still on, right?
Yeah.
So you can pass the entire thing to the other side. All right. So this is shorted to where? Shorted to the gate of this sampling transistor. So VG is what?
VDD plus VC.
All right. Are you having a constant VGS for this sampling transistor?
Yes.
Yes. So during this phase, what's happening at the capacitor here? What's happening? There will be some internal resistance, but so anyway, so it's charging up this one with a finite amount of time because there's a little resistance over here. It's the RC delay, but anyway, so this signal will charge up the cap. So during this phase, whenever these two, the signals are the same phase, when this signal is 0, this capacitor is doing what?
It's charging. Or it's like,
Charging up, following what? So if I say this is a sample, track, and hold circuit, so if these two are zeros, which phase or which operation is this in?
this is a sample, right? Because it's sampling the current signal and like saving it.
Yes, sample, that's right. What about track? Is it able to track? If the signal, for example, there's a sound wave, start going up, right? Start going up. What's happening here? If this is start going up, like a sound wave, just this part is going up, right? Going up. Yeah, so whenever there's 0, there's a VDD over here, and then this starts going up as well because this is on, right? This is on, and there's no distortion because it's a constant VDD, and this will pass, right? And charges up. So you will see a little bit delayed, but not getting distorted as well. Okay, so the capacitor is sampling from starting from here and then tracking whatever the signal is going, still keep going up. It's going to track as well. And whenever this is going up, it passes through these transistors and adding to this VDD, so it's bumping the VDD up as well. So the VDD is not the floating VDD, so it's adding that signal, this little thing, to the VDD, right? So starting, adding to it. And this one passes through all the transistors and reaching this one and forming a constant VDD, so it's not getting distorted, and it's nicely tracking it. Okay? So once this one becomes 1, what's going to happen? So after that 0 cycle, the 5-bar signal becomes 1. What's going to happen? Let's see. Do you still have to worry about this one? Yes, because this is going up, it's pushing this point. So this voltage becomes what? It's pushing. It's pushing.
2 VDD? Wait.
This is 2 VD, right? It's become 2 VD. This is become 2 VD. Okay? This is become 2 VD. Okay? 2 VD. Then what? This is a rising edge, so this NMOS is on. You got a channel. It starts doing what?
Discharging to the ground.
It's like a waterfall, right? Boom. Go to the cap. This is the wide open. You can just dump the entire VDD to this capacitor. Just keep dumping, right? Okay, charging up. It's waiting for this one goes to 0 again, and it's store floating VDD. Okay, but before that, it's charging up. So when it's charging up, what's happening over here? This is 1, right? This is 1. Ground will be passed to this point. So previously stored a VDD plus VSIG. Even though, can you control this one? I mean, the analog voltage keeps coming in. Are you able to stop it? No. You're not stopping it. It keeps coming in, but the thing is, it's not taking it anymore, because if this is off, this one being reset, okay, because it's shorting to ground, and this NMOS will be off. Okay, it just directly, whenever this becomes 1, at that moment, immediately, the voltage here will be what? So so here, right? So we're talking about this signal is getting sampled and tracked, right?
Yeah.
And after that, I mean, the analog input is not getting controlled; it keeps going up. But at that moment, this one, there's a folding edge, right? What's going to happen after that point? Here, hold. Okay, because this is off, right? So this will be hold. It's going to become the folding charge. So it's whatever the right before that point, whatever the voltage is going to be held over there. Make sense? And now if we go back to the one of the simulation results. Jesus, I'm so hungry. I'm trying to eat less. Downside is just become so hungry. So look at this one. Look at this one. So here's a sample hole. That's a phi signal, right? That's phi signal. It's gonna invert it. You can tell, right? It's gonna invert it.
Yeah.
So now you have a rising edge, then it starts holding it. That's not a big deal. You can always invert it, right? If you invert it, it becomes a falling edge to hold it. Okay? You can see here, I start sampling it, starts tracking. Start sample, get sample, right? It goes up, and then start tracking, right? So the black one and the red one, which is tracking which?
The red is tracking.
Yeah. Okay. So tracking, right? Tracking and then being held over here afterwards, right? Okay. Any question on this circuit? Clear?
I think so. And so,
Right. Huh?
so yeah, this would be an analog to digital converter, right?
No, that's a Simon hole.
Sample.
That's this part. This part.
Okay.
So for the ADC, we need these. Because this one's output is still analog voltage. It's not converting to an 8-bit digital voltage, right? It's still one pin, but analog, right? It's being held over here. So we need the following circuits. So very important one is the timing circuit over here. I think so. This guy. So I'm trying to optimize it. So the one we used in the last few semesters, it sort of worked, but it's still always getting a lot of errors. But you can see that that's the op-amp issue for the lower voltages. It's not really tracking. But for the other ones, you can see if I drew a line, it's able to track it. If you zoom in, you are able to see that it's getting, having the steps to follow it. And if I input a sine wave like this, you can ignore these ones because you can always filter them out. Use a low-pass filter. You always see these big spikes, but that's okay. So there's a sine wave with the V in. Couldn't see it's behind it, so that's a sine wave. And these are all the digitized converted results, and then being converted back using a DAC. Okay, so you got an ADC. ADC's output is a digital signal 8 bits, and then you feed that into a DAC to convert it back to analog, which is this guy, the blue one, and see if you can recover it. So that's what I was trying to do. But it worked to some extent, but it has some issues. So I'm trying to fix it, just a little bit tweak to the timing. If we can fix it, we'll probably try to tape it out. If you guys are interested in the future, we should do it. Otherwise, if it's not successful, we'll just stick to the old design to let you guys just lay it out. Probably not 8 bits, can be 6 bits, can be 4 bits. 8 bits is a little bit too much, but if this is modular design, it shouldn't be that bad, right? So basically, the D flip-flops is just this TI D flip-flop we learned, and you can see the circuits here. The timing, it's a few gates. These is the counter. We'll cover counter next time. It's the counter, and it's just D flip-flop, just a couple of D flip-flops, very easy. And these are just 9 gates inverters. That's for the timing block, which is the timing block, this guy, right? And the inverter, the sample and hold circuit, which is the one we just covered, not too many transistors as well. And the op-amp, the circuit is given, so you guys are not really designing too many of these. So the inverter, the op-amp is a competitor design. It's very classic. We don't really have to change anything. And that's the SAR block we learned, the sequencer and code register we covered, a few weeks ago. Okay, and the DAC, it just all the DACs, we use the same DACs for the R2R resistors. And that's the 8-bit D flip-flop array. If you get one D flip-flop done, you can use it for so many different places. It's just replicating, copy and paste. Okay, it's not a huge circuit, but a lot of fun, I believe. Okay. So next we'll talk about DNLs and NLs. So if you design an ADC, you want to characterize it, see how good it performs. If it works or not, you want to look at the nonlinearities. So look at the handout over here. So for DNL, I think this one only covers DNLs, or DNLs and NLs for the DAC. So we'll talk about the DNLs for NLs for ADCs next time. But for the DAC, you can see DNL is called differential. You can write it down since I don't think they spelled it out. So it's a differential nonlinearity. It's called DNL. This could be an interview question. So we'll ask you, hey, what's the DNL and the NLs of your ADC? So differential nonlinearity is called DNL. And the way to calculate it is like this. So these are a few pages from the textbook. Ideally, definitely, this is ideal line, but it will never happen because you always have finite resolution, number of bits for the ADC or DAC. So this is the 8-bit one, but for the 8-bit one, the best you can get is have all the points directly on the line. However, it's not always the case. So if it's the DAC, the input is digital inputs, right? You can see the x-axis is the digital inputs, right? Digital inputs. Starting from 0, 0, 0, definitely you are expecting a 0 output for the analog output. So these are VL over VREF, but you can convert it to the actual analog voltage if you're assuming 5 volts, right?
Yes.
So how do we convert it?
You just multiply the fraction.
It's a 5 volts divided by the whole resolution, which is 2 to the 8th, right?
Yeah.
And times 1. Oh, 3 bits, I'm sorry, 3 bits. 2 to the 3rd, which is 8. So 5 is the whole entire range, voltage range. And this is all the steps, 8 steps. 5 divided by 8, which is 1 LSB's voltage. Okay? So actually this should be this voltage. But they use a different number to represent it, which is fine. Okay? So all, for example, 0, 0, 0 should expect this output. And what is this? Is that 0.625? 5 over 8. Yeah, 0.625. Yeah, you'll deal with this number a lot, so remember it. So this is the LSB of the 3-bit ADC or DAC we are dealing with. So this is the voltage we have, which is this guy. Alright? And this is this divided by 5. Right?
Yeah.
Okay. And then you have this 0, 1, 0 as a of the DAX input, and you are expecting this one ideally, and so on and so forth. So this line, so all the dots should fall onto the line, but actually it won't be the ideal case in real life. So we have this is fine, but this guy goes up. All right. So for DNL compares to the ideal step size. And the final result is represented in LSBs. So I have to compare. So in that case, the best way to do that is you find out the step size you have, the actual step size, and then you subtract the ideal step size from it, so you can find out the difference from the difference from your step size compared to the ideal step size. And these step sizes should be in the unit of LSBs. Let's take one example over here. 0, 1, 1 is the number 3. So we can call it that at that point it's the DNL 3. DNL 3 is the actual step size. You can see it's 1.5 LSB, What's the ideal step size? Definitely 1 LSB. So your DNL3 is 0.5 LSB. What about DNL4? Even though it falls onto the curve on the line, however, the step size is not correct. So we're talking about from the previous one to the current one, it seems like there's a 0.5 LSB, like this point. It's just telling you that. You don't have to measure it. There's no way to measure it. It's just telling you, hey, from here to here, it jumps for 0.5 LSB. Okay? So for DNL4 is 0.5 LSB. That's the step size you observed, minus the 1 LSB, the ideal size, which is minus 0.5 LSB. What about DNL5? DNL5 is 0.25 LSB as observed. Okay, it's just this point compared to the lower point. It's 0.25 LSB. So 0.25 LSB minus 1 LSB, which is giving you minus 0.75 LSBs. And then DNL number 6 is 1.75 LSB minus 1 LSB is 0.75 LSB. And DNL7 has the ideal height. So DNL7 is 0. So there's no DNL 4.7. And you can put all the DNLs, the points, and you can plot a DNL curve for that. So which looks like this. Okay? So you can see the papers. Let me see if they did it over here. They should. If they didn't, that's weird. They should. There's no internet connection again. Let me try to find this one. Barely.
What's the internet's not feeling it today?
Yeah, anyway, we'll wait for that a little bit. All right. So you can expect all the publications, the scientific research papers that evaluate the performance of the ADCs or DACs, they will plot DNL to INLs, right? To tell you the quality of it. And for INLs, it's called integral nonlinearity. It's INL. That compares your converted results to the ideal results on the line instead of the step size. So you can see, look at this curve over here. So you got the point to here, and then minus the ideal value on the curve, on the line. Okay, to get an NL. So for this one, is it still the same problem? Is it the same problem? 28.14. No, it's not a problem. Same problem. Anyway, we can look at this one. So what are the NLs? Hey, just look at the points. See if the points you are getting from the converter. So the points are on the curve, right? On the ideal curve. If it's not, there's an NL. If it's on the curve, there's no NL. Different from the DNLs. So you can see the DNLs. Even though the point is on the curve, as long as compared to the previous point, the step size is larger than the ideal step size, you are getting a DNL, right? It's compared to the step size. But for this one, if it's on the curve, there's no NL. All right, that's the difference. So you can see here, this point is 0.5 LSB up compared to the point on the curve. So you're getting a 0.5 LSB NL, which is NL1, right? NL1 is 0.5 LSB. And for here, you got a NL3, which is also 0.5 LSB. And this is NL5. It's 3, this is 5. So 5, you use this one minus the point on the curve, which is the negative value. It's a negative 0.75 ISB. Okay? So if I give you an example like this, it's going to be a very similar example like you can see on the quizzes or exams. I list a table over here. You'll be able to find out the DNLs and NLs from it. If I say digital input, and voltage output, and I also listed the ideal output for you. Zero, 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 definitely that's a DAC, right? 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1. Zero, 0.625, 1.5625, 2.0, 2.5. Am I missing a digit? Yes, I am. Three 3.125, 3.4375, 3.375. And these are the voltage output you observed, you measured. But ideally, the values should be this. It's adding 1 LSB each time. Let's try to find DNLs first. A couple of them at least. Couldn't finish everything. We'll keep doing this on Friday, on Wednesday. But let's find some of them. See if you guys can figure out how to do it. What's the first one?
The first one was the third number.
Mm-hmm. That's DNL what?
DNL
2.
2.
So how to find the step size?
It should just be 1 LSB. So
Number 2 to the third.
Yeah? This minus this, right? That's the step size. So DNL what? 2 equals 1.5625 minus 0.625 over what?
2 to the third.
Hmm? What's
Like 2 raised to the third, or no? For the subsize.
Because the subtraction is telling you the difference of the voltages, right? And if you find out how many LSBs are in this voltage, how do you find out? Divided by what?
divided by the LSB.
Yeah, so what is the LSB? Yeah, 0.625. So that's how many LSBs of that difference. And that's your actual step size. And you if you want to find the DNL, you want to minus what? 1 LSB, just 1.
Yeah.
So that will be your final DNL.
Well, it'd just be minus 0.65.
No, because the unit is 1 LSB. And you are dividing this, and eventually you are getting how many LSBs actually. Because this is the 1 LSB's voltage. This is the voltage over here, and that's 1 LSB's. So this is how many?
It's greater than 1.
Huh?
It's greater than 1.
Let's put a unit here.
Yeah.
Does that make sense?
Yeah.
What's the next one? Look at step size. Just compare, right? Here to here.
Yeah, it's
Here to here. What's the difference? This is like a 1.625, 0.625. That's the ideal one, right?
yeah.
And this is 0.4 something,
0.44 or something.
right? So there's a DNL here as well. So that's DNL what?
DNL3,
3 is what? 2.0 minus
1.5625.
divided by
0.25.
minus
1 LSB.
okay. So usually I have a homework assignment on this and I'm gonna post it later. So I think we should have you guys work on the I'll post it later, don't worry about that. There will be something in there. But we'll keep working on this on Wednesday and so we will be able to know how to calculate DNLs from the table like this. And also we'll move on to ADCs, very similar way to calculate it, how to do ADCs DNLs. Right?
Yeah.
So now internet is available. Let's look at the paper really quick. Still have 2 minutes. So that's the 1999 paper on the sample and hold circuit. And you can see they plotted these ones, right? LDLs. And it's pretty good because it's within 0.5 LSB. A little bit larger than that. If you see, if our DNLs are like 3 LSBs, 10 LSBs, it's probably filling.
Yeah, it's probably.
Yeah.
So the INL, you just find it by basically subtracting the ideal value minus the like given value, correct?
Yeah.
Okay.
Yeah. All right. We'll see you in the lab tomorrow, and I have to set up accounts for you guys, so I'll have a really busy afternoon today. All right.
Setting up cadence and all that?
Yeah.